Nuclear energy is a safe, sustainable, reliable, and economically viable source of a much-needed energy and allows us to mitigate climate change. Here is a nuclear power plant. The energy is produced by the fuel inside the reactor core. Let's zoom in. The fuel is contained by the cladding, which prevents the release of the fuel material and is thus one of the main safety features of a nuclear power plant. But despite its great properties, the cladding undergoes corrosion because of the surrounding water. Hydrogen is created as a byproduct and is then picked up by the cladding. Once there is enough of it, the hydrogen precipitates into brittle hydrides that are shaped like platelets. Their orientation depends on the conditions of the precipitation, and it is important because hydride orientation dictates their effect on the fracture behavior of the cladding. My research aims at answering the question, what explains the orientation and the morphology of the hydrides? A lot of experimental data is already available and answers part of the question. But even if some computer models already exist, a quantitative model able to predict hydride morphology and orientation in a reasonable time is still missing. What we did was to develop a new model. We derived new functions to describe our system and new equations to determine its evolution. It appears that this model can be up to 800 times faster than previous quantitative models, so it really accelerates the research. However, there is still a lot to be done. Now that the model has been developed and tested, we need to compare its predictions to experimental results and add new physics to make these predictions more accurate. The main impact of my research will be to accelerate the research in microstructure evolution and help us understand and predict the changes in mechanical properties of the very important safety feature that is the cladding.